All right, let's start the second day of crypto. Welcome to this morning plenary session, which is the best paper session. We will have two papers in this session, the best paper and the best early career paper. Before we start, I'd like to just make a little announcement for speakers to check, please, that their slides are always the latest version that they sent in, because we have no way of knowing that this is the latest version. So there will be a version, but please check it's the right one before you speak. And the second thing is that for those that haven't sent in slides yet, please do so, because we're still missing a couple of slide sets for tomorrow and for Thursday. All right, so coming back to our topic, best paper session. So there are two presentations in this session, best paper and best early career paper. And one more little announcement before we start. Actually, there is a third paper that I'd like to mention that is going to be presented later today in a follow-up session, which is the runner-up to the best early career paper, which will get presented somewhat later, not in this session. So if you're interested in that one as well, please go see it later. So with that, we can start with our best paper, which is Fast Practical Lattice Reduction through Iterated Compression by Keegan Ryan and Nadia Heninger, and Keegan is giving the presentation.
All right, thank you. Yes, my name is Keegan Ryan. I'm a PhD student at the University of California, San Diego, and my main area of research is cryptanalysis. Now, through my PhD, most of my projects have involved lattice reduction in some way, and I think it's a little bit surprising how frequently lattice reduction appears when doing cryptanalysis. So this was observed in 2001 by Nguyen and Stern, who wrote about the two phases of lattices in cryptography. Now, in the first phase, we can use lattices to build secure cryptographic systems. These systems, such as the post-quantum cryptography schemes, are based on a sort of exact lattice reduction problem. This problem, the best algorithms that we have, take exponential time, so we believe that these schemes are secure. But there's also this other phase of lattices in cryptography where we can do a sort of approximate lattice reduction. And for these problems, we have a polynomial time reduction algorithm. So this is frequently used for cryptanalysis. So it shows up when doing side channel cryptanalysis of RSA, DSA, and DC-DSA. Approximate lattice reduction can be used to break some schemes outright, like knapsack cryptography and some older FHE schemes. And approximate lattice reduction also shows up quite frequently when doing computer algebra. So this is the traditional picture of the dichotomy of lattices in cryptography. But there is a problem with this picture, because in theory, approximate lattice reduction takes polynomial time and is therefore efficient. But the degree of this polynomial is large. So in practice, approximate lattice reduction is often a bottleneck for doing cryptanalysis. So that's the goal of this work, is to take these approximate polynomial time lattice reduction algorithms and make them more efficient in practice. So this has been a goal for a while, beginning with the algorithm of Lenstra, and Lovaas in 1982, which for a lattice basis of dimension n and entries of bit length p takes time approximately n to the 5 p squared. So because of this dependence on the dimension, this is only efficient for small dimension. In 2009, this was improved by Nguyen and Saleh, who created an algorithm that takes time n to the 4 p squared. And because this algorithm allows implementations to use hardware floating point numbers, this is quite efficient in practice and what's actually used by many people with implementations such as the popular library package FPLLL. This implementation is able to scale up to around dimension 200, so about an order of magnitude better than the original LLL algorithm. The best proven running time for lattice reduction is due to Nomeyer and Saleh from 2016, and their algorithm takes time approximately n to the 4 p. But because of challenges in implementing this algorithm, it's also only useful in small dimension. Now, our algorithm takes time n to the omega p, which is roughly the cost of a matrix multiplication for common applications. And this means that our implementation is usable for bases that are an order of magnitude larger than the previous best. All right, so just as one example of why this sort of improvement is important, we can look at the fully homomorphic encryption scheme of Gentry-Halevi. Now, this scheme is based on ideal lattices, and in 2010, Gentry-Halevi published a set of encryption public keys as a challenge to those trying to cryptanalyze the system. Now, it turns out several of the parameters that Gentry-Halevi used were susceptible to a polynomial time lattice reduction attack and could be broken. But despite this, it was still extremely hard to break these in practice. So for these parameters, the toy parameters were broken in 2015 by Plantard, Cecilo, and Zhang in 24 core days using FPLL, a modified version of it. They conjectured that the small parameters could be broken in 15.7 core years. And then separately, Chen and Nguyen in 2011 estimated that the medium parameters could be broken in 69,000 core years. These are new algorithm and our new implementation. We can break the toy, small, and medium parameters in 15 minutes, 31 core hours, and 6.4 core years, respectively. If you would like to check our work on this, here are the solutions to the Gentry-Halevi challenges. All right, so it's clear that our algorithm can be up to 10,000 times faster in some cases, but the remainder of this talk will address how this is possible and why we can do this. So I'm sure many of you are familiar with this image of a lattice, and you can think of a lattice as an infinitely repeating grid of points in n dimensions. Computationally, we represent a lattice by its basis, where the points in the lattice are integer linear combinations of the columns of the basis. Now, in dimension 2 and above, there are infinitely many different lattice bases that represent the exact same lattice. So lattice reduction is the process of finding a different basis that has better computational properties. To be a bit more precise, we're looking for a basis that has vectors that are short and nearly orthogonal. So to measure orthogonality, we can use something called the Gram-Schmidt orthogonalization, or GSO. And if we take the log lengths of the Gram-Schmidt vectors, this gives us something called the profile. And because the profile is connected to orthogonality, the profile can tell us something about how reduced a lattice is. And if we animate the profile as the basis changes during lattice reduction, then we can see how close we are to achieving a reduced lattice. So we can take this technique and apply it to the LLL algorithm to see how it manipulates a basis. With the LLL algorithm, we can see that it operates on pairs of column vectors at a time. And as it changes those vectors, it changes those corresponding entries in the profile. The LLL algorithm repeats until two conditions are satisfied. There's the size reduction condition and the Lovász condition. And I have both of them written on the screen formally, but the important takeaway is the effect that the Lovász condition has on the profile. Because the Lovász condition implies that after reduction, there are no large decreases in the profile. Small decreases are fine and absolutely expected by this process, but large increases are also okay. So if you see the profile after reduction here, there are small decreases in the profile, and then it ends with a large increase. And this is because it's Lovász reduced. All right, so we've already discussed why LLL lattice reduction is that it is slow, and there are two main strategies for making LLL faster. The first strategy involves using recursion. So recursion allows you to do fewer full dimension GSO calculations. So this is done by doing recursive calls to a sublattice reduction, and overall you do fewer arithmetic operations. The other main strategy for improving lattice reduction is from precision management, where we take the especially large entries in the GSO and we represent them using floating point values. The challenge for this precision management strategy is knowing exactly how many bits of precision we need to represent these values. So both of these strategies improve the asymptotic running time of lattice reduction, and both of these have evolved independently in the literature. So each algorithm will use one or the other strategy. So the natural thing to want to do is to combine these two strategies together into a single fast algorithm. But this is exceedingly difficult and very challenging to do. This is the exact problem that was approached by Kirchner, Espetow, and Fuchs in 2021, where they wanted to create a fast algorithm that combines these strategies of recursion and precision management. So they made two observations to approach this. First, they observed that the precision required depends on what they call the spread of the profile, or the difference between the maximum and minimum values in the profile. So it's an easy way to determine how many bits of precision you need. Secondly, they performed lattice reduction on a class of lattices known as random q-ary lattices, and they made the following heuristic observation. With every iteration of their algorithm, the spread decreased exponentially quickly. And this is an approximation of what their heuristic is. And as it decreases exponentially quickly with each round, that means the working precision decreases exponentially quickly, which means operations become exponentially faster over time, which means that the algorithm terminates rapidly. So if you take this and you assume that their heuristic observation translates to all lattice bases, this gives you the result that the running time of lattice reduction is n to the omega p, about the cost of a matrix multiplication. So these authors publish their algorithm. They have an implementation. So we take their implementation and we run it on cryptanalytic test cases that we care about to see if we can actually finally solve these challenges. But unfortunately, their approach fails. And if we look at the profiles of these cryptanalytic test cases, we can clearly see why. So there are several different types of profiles for several different types of applications for using lattice reduction in cryptanalysis. And recall that the Lovász condition implies that there are either small decreases in the profile or there are large increases. And the heuristic assumption of KEF implicitly assumes that there are only small decreases in the profile. So where for some cases this is true, that there are only small decreases and the heuristic assumption of KEF is true, for many of these test cases, that assumption is false. So to see why this is a problem a bit more clearly, we can look at the performance of their approach on a n-true-like lattice as generated by FPLL. As the algorithm progresses, you can see that there are these large increases that appear in the profile, which mean that the spread, or the difference between the minimum and maximum values of the profile, never decreases, and it certainly doesn't decrease exponentially quickly. So the working precision never decreases, the operations never get faster, and the algorithm can be quite slow because of test cases like this, and all because that heuristic assumption does not hold. So we need some way of dealing with this sort of problem, and we need some way of handling large increases in the profile in order to have a fast lattice reduction algorithm for cryptanalysis. Fortunately, we find just a solution in the literature with this paper from Cerrucci, Morel, Soleil, and Viard. They observed that you can scale the basis vectors of a lattice independently in a way that respects lattice reduction. And if you take this scaled basis, which has smaller entries, and apply lattice reduction to it, then you can take the result of that lattice reduction to reduce the original larger basis. So because you're taking the same geometric information, but using fewer bits to store it, this is essentially a compression of the lattice basis. If you look at what happens to the profile, you can see that those large increases in the profile are squashed down and decreased. So the spread is smaller, which means that fewer bits of precision are required for the GSO. So this gives us the basic outline of our algorithm. We take the framework of Kirchner et al., and after every iteration of recursive calls, we apply the compression strategy of Cerrucci et al. We repeat this process of recursive calls and compression until the lattice basis has a small compressed spread. And if we see how this performs on the same n-true-like example from before, we can see that over time, our spread with compression decreases quickly, which means that our operations are going faster and the algorithm terminates more quickly when compression is used. So our algorithm is easy to state, and it's clearly faster on its test case, but that's not the challenge of this work. The main challenge is showing that this is fast for all lattice bases. And there are several challenges to doing this. First of all, we need to actually show that the lattice bases that are output by our algorithm are actually reduced. Now, it was observed in 2001 for their recursive reduction algorithm. Coy and Schnorr observed that it's impractical for their recursive algorithm to achieve the Lovász condition. So recursive algorithms in the literature have worked around this problem by doing away with the Lovász condition as a condition for their reduced bases, and only assuming and only showing that there's a bound for one of the vectors of the output lattice. But this isn't good enough for us. For cryptanalysis, frequently you require multiple bases to be bounded. So what we do in our paper is we show that the notion of a compressed spread, like the bases output by our reduction algorithm have, leads to the same bounds on all of the basis vectors that the Lovász condition implies. So our bases are essentially as reduced as Lovász reduced bases and as useful for doing cryptanalysis. All right, another problem that we need to tackle in this work is the question of whether or not our algorithm is numerically stable. So this is an issue because every time we apply the compression operation, we introduce a small amount of error. And you can think of this like the error from a floating point calculation. And because we're doing this compression in an iterated way and doing it multiple times over the course of our algorithm, we need to make sure that the error doesn't balloon out of proportion and become too large so that we no longer achieve a correct solution. So we look to the literature and we find that there are, in fact, perturbation analyses for LLL, but these analyses require the Lovász condition to hold, which we've already seen is incompatible with recursive algorithms. So using these rigorous bounds won't help us. What we do instead is we develop our own new definition of error in lattices, and we use this new definition to show that our algorithm is in fact stable because the size of the error grows logarithmically with the number of compression operations. So our algorithm is stable, and our algorithm does return correct results. But the most challenging problem that we face in showing that our algorithm works for all bases is showing that our algorithm is fast. And the reason this problem is so difficult is because the exact behavior of the algorithm depends so significantly on exactly what the profile is doing. And we already saw that for all the different cryptanalytic test cases, the profile looks incredibly different. So that means that the sequence of recursive calls looks incredibly different, and it makes it very challenging to bound the running time. So the way other works have approached this issue in the past is they either used weak heuristics that aren't true in all cases, or they use weaker definitions of what a reduced lattice basis is, neither of which will help with what we want to do here, which is cryptanalysis. So the approach that we take here is that we show that the compressed spread of the sublattices that are reduced by recursive calls can be used to bound the behavior of the profile over all possible types of profiles. We also use heuristic assumptions that are significantly weaker than the heuristic assumptions that are used previously. And throughout all of our extensive experiments, these heuristic assumptions hold in practice. Putting these two things together, we see that the running time of our algorithm is n to the omega p for well-conditioned bases, and slightly larger for ill-conditioned bases, which are rare in practice. For the full expression of the running time, we'll refer you to our paper. All right, so our lattice reduction algorithm is fast, it's stable, and it returns a useful solution. So what we need to do now is we need to implement it and actually use it for cryptanalysis. So our implementation, we call FLATTR, for Fast Lattice Reduction. And the goal of FLATTR is to provide an easy-to-use interface for doing lattice reduction, just like FPLL, where you don't need to be an expert in lattice reduction to be able to use the tool. So during the course of development of FLATTR, we continuously tested on numerous different cryptanalytic test cases. So we could see that FLATTR was fast in practice, it was numerically stable, and returned solutions that could be used to cryptanalyze these systems. Now, FLATTR calls out to the BKZ implementation of FPLL, which means that the approximation factor that we get out of FLATTR is very good in practice and as good as you would get by using FPLL, but our algorithm converges much more quickly. Our algorithm is parallelized because we track the data dependencies present in our update and compression algorithms. And our algorithm, implemented in C++, is currently available on GitHub. So I welcome you to go download it, compile it, make pull requests, and use it for your own research. So since publishing a preprint of this work, we've been in discussion with both FPLL and q-ary to implement this algorithm in their software as well. So hopefully it will be even easier to use this algorithm in the future. All right, so we've got our fast algorithm. Now, how about we look at some test cases? So we look at several test cases in the paper, and one of the important test cases to look at here is the same test cases used by the KEF paper in 2021, random q-ary lattices. So as seen before, these have a very predictable behavior during lattice reduction and a very predictable decay in the spread. So compression isn't strictly necessary here because we don't have those large increases in the profile, but we wanted to see how our algorithm compares anyway. So we evaluated the performance of our algorithm in our implementation compared to the implementation of KEF and the implementation of FPLL. And if you plot the running time on a log-log plot, you can see that FPLL in green is asymptotically slower than either KEF or our implementation. And you can see that even though our implementation is slightly slower in small dimension, the implementation of KEF does not reduce bases larger than dimension 256 in reasonable time, whereas our implementation can easily handle bases of size 2048 or larger. So that's random q-ary lattices. We can also look at the Gentry-Halevi lattices for the FHE problem. So you can already see by the evolution of the profile that this starts out different from the q-ary test cases, where we're focused on the left side of the profile at the beginning of the algorithm. We can once again plot the performance of our implementation against the implementation of KEF and the implementation of FPLL on a log-log scale. And again, you can see that our implementation scales to much larger dimension. So this graph goes up to dimension 2048. And you can see that the implementation of KEF only makes it to dimension 128 and implementation of FPLL to dimension 256. So our implementation scales to much larger dimension and is significantly faster than either of the alternatives. Now, you'll see that the dimension 8192 test case for corresponding to the median parameters of Gentry-Halevi parameters is not here. This is because that was multi-threaded, and this chart shows the single-threaded performance. And we had to do some crazy things to get the solution out for the medium challenge. Because of an error that we had introduced that we had later fixed in the code, the algorithm wasn't going to terminate quickly enough when the lattice basis was actually reduced. So we watched the profile to see when the profile was actually reduced enough. Then we went in with a GDB script to extract the lattice bases out of memory, convert that to the actual solution of the Gentry-Halevi challenges, and then be able to post the solution. So without that, we would have had to have wasted another 6 months doing this calculation. All right, and the last test case that we're going to look at during this presentation is that of RSA partial factorization. So you can see by the evolution of this profile that there are many large increases in the profile, which tells us that compression is especially useful for this test case. We use the idea of coppersmith and an implementation and a construction of Palgrave-Graham. And again, if we plot the performance, we see that the implementation of KEF does not extend beyond dimension 19. And even though FPLL is able to handle most of the same test cases, our implementation is orders of magnitude faster than that implementation. So we have many more experiments and test cases in the full version of our paper, and I recommend that you check them out. But I just wanted to end with some further applications because the whole goal of this was to be able to do cryptanalysis for my own research. And that has been the case since creating this implementation. We have this paper from PKC this year where we had to do the implicit RSA factorization problem, which involved reducing a lattice of dimension 465. That was easily doable with flatter. We have this other paper where we're cryptanalyzing a RSA-based random number generator, which involved reducing a dimension 1443 lattice, which we can do with flatter. We have this other paper to appear at CCS, which involves reducing a lattice basis with large entries. And since publishing our algorithm, other people have reached out to us and said that they've been using flatter for their own research. So there are many other examples, and if you have examples, I would be incredibly excited to hear about them. So this project spanned researching lattice reduction algorithms, combining the techniques of recursion and precision, testing on different test cases, creating a fast implementation. And in the end, we can say that lattice reduction is no longer just fast in theory, but now it's also fast in practice. And throughout the course of my PhD, this ability to do fast lattice reduction has been incredibly useful. Now that both the algorithm and the implementation are available publicly, we look forward and hope that this algorithm can be useful to you as well. Thank you.
Okay, I think we have time for 1 or 2 questions. If there are questions online, you can also, you can type them in chat. I will be able to see them too. I see Kevin and Shai coming up. Kevin? Nope.
How about now? So I have a question about the parallelism. I assume it's a shared memory implementation. I wanted to know what are the limits of how much do you gain by parallelism, and are there opportunities to improve the parallelism?
There are absolutely opportunities to improve it. Our implementation of parallelism is not great. So sort of where it benefits is there are some operations in the update step that are easily parallelized where each vector is independent. But the more challenging steps are things like q-ary factorization, where the parallelization doesn't scale as well. So for our implementation, for example, with the dimension 8192 Gentry-Halevi test case, we didn't get the same level of parallelism that we have the number of cores on the machine. So there's definitely room for improvement there. But it does give you a noticeable speed up on most common machines that people will be running this on, so laptops and servers.
So how much faster by parallelism?
It depends on the exact structure of the lattice basis, but probably between 2 times faster to 10 times faster. It depends on how many cores you have. Yep.
Wonderful work, thank you. Actually, 2 questions. One is whether any of these ideas is useful also to speed up the block reduction at the end. And 2 is, are there any implications to the lattice security estimator and the dimensions of lattice-based crypto systems?
Yeah, can you clarify what you mean by the block reduction?
At the end, when you do the BKZ reduction, can you use the same type of ideas to do the BKZ reduction with larger blocks, for example?
I see. That's not something I've spent a ton of time thinking about, but essentially you can mix and match these different algorithms. So BKZ, which achieves the better approximation factor, you can use this to do your recursive calls, and you can sort of increase the block size of BKZ that you use over time. So in our implementation, we do sort of use this progressive strategy that was also used by the KEF paper, where over time you do a better and better approximation quality, which will correspond to using a larger and larger block size of BKZ over time. Your second question was about the lattice security estimator. We have looked at this, and we don't think that there is a significant impact on this, because from our understanding, what the algorithm does is they are based on sort of the hardness of these exact lattice reduction algorithms. And one of the models that they use for this cost estimator is the cost of a single enumeration call in a particular dimension. So while there are other models that assume that there's a polynomial number of calls, which would still be true with this new algorithm, even though our polynomial is smaller, the exact algorithm that I think that estimator uses is just assumes that there is one call. So that is a very conservative estimate that is not affected by our work.
Any other questions? No, I don't see any online either. So let's thank our speaker again. And will be shown at 11:15 later today. Okay, we have Elizabeth on stage. Take it away.
So first of all, we would like to thank the chairs and the members of the program committee for giving us the opportunity to speak about this work today. This is joint work with Chelsea Komlo and Mary Maller. And today I'm going to be talking about Schnorr threshold signatures. This is a very active area of research at the moment. And in this talk, we're going to be focusing on some of the stronger notions of enforgeability that we can achieve for these schemes. So first of all, why are we interested in Schnorr signatures in particular? There are 3 signature schemes that are currently standardized by NIST: RSA, ECDSA, and EDDSA. So EDDSA was added in August of 2022, and it is the deterministic version of Schnorr. Now, it is not verifiably deterministic, so the verification for Schnorr and EDDSA are the same. RSA signatures are much larger than Schnorr and ECDSA signatures. So for 128 bits of security, you would need 512 bits for ECDSA or Schnorr signatures versus 3072 bits for RSA. ECDSA was designed to get around the patent for Schnorr signatures, so it introduces a number of complexities, including nonce inversion. And what this means is that there isn't a nice security reduction like we have for Schnorr. So we have a reduction to the discrete logarithm assumption in the random oracle model. And I'd just like to mention BLS. BLS is not standardized through NIST, though I hope this changes in the future. BLS is slow to verify. But there is a very nice paper by Bacco and Loss at CCS last year, which proves adaptive security of BLS. Okay, so what is a threshold signature scheme? So the idea of threshold cryptography is that we don't want the secret key to exist in one place. We want to somehow distribute that key amongst a set of parties. So the parties can engage in a protocol to produce the overall secret key and public key representing the group of signers. This could be a trusted key generation protocol like Shamir's secret sharing, or it could be a distributed key generation protocol. So once the parties receive their shares, then T out of N parties are able to issue a signature, and T minus one or fewer of them cannot. Let's look at the timeline of this research. So Schnorr signatures were invented in 1990, and they were first patented in Germany and then in the US in 1991. We see the first threshold Schnorr scheme by Stinson and Strobel in 2001. And the idea there is to actually use a distributed key generation protocol within the signing itself. In 2008, the Schnorr patent expires, and then there's a bit of time that passes. And in 2018, there is a flurry of activity around building multi-party Schnorr schemes, and this is because they are being used to secure cryptocurrency wallets. So the first scheme in 2018 is a 3-round MuSig. So this is a multi-signature that differs from a threshold signature in that all N parties are required to sign instead of T of them. In 2020, we see the first 2-round schemes. So MuSig 2, DWMS, and the threshold scheme Frost. And in 2021, we introduced an optimized version of the Frost scheme called Frost 2. Also in 2021, Bitcoin moves away from ECDSA to Schnorr signatures through the BIP 340 proposal. In 2022, I mentioned that NIST standardized EDDSA. And earlier this year, they put out an initial call for threshold schemes, including those that output a Schnorr signature. So you can find the document here at this link. And there are a couple of different main goals that are specified in this document, which are kind of the main driving force behind this research. So the first requirement is that the threshold scheme needs to output a Schnorr signature, and it needs to look exactly like standard single-party Schnorr. So this means that not just the signature needs to look like standard single-party Schnorr, but also the public key. We're also interested in schemes which have few signing rounds, and here we're going to be looking at 2- and 3-round schemes. So I mentioned that the first scheme by Stinson and Strobel used a DKG within the signing itself, so it incurs 4 more signing rounds. We're also interested in reasonable security assumptions, which I'll talk about later. Now, the 2 stronger notions of enforgeability that we're going to capture here are concurrent security and adaptive security. So a concurrent adversary can open multiple signing sessions at once with potentially different sets of signers and engaging in multiple rounds of signing. And we need to mitigate against an adversary who can use this added capability to forge a signature. Our strongest notion of security that we show in this paper is adaptive security. So an adaptive adversary can not only corrupt parties at the beginning of the protocol, but can actually corrupt them as the protocol progresses. So again, there may be multiple signing rounds, multiple sessions, and at that point, the adversary can use the information that it's seen so far to decide who it wants to corrupt. So let's first look at how standard single-party Schnorr works. So the signer here is going to sign produce their secret key by sampling an element uniformly at random from a field. And their public key will be the generator raised to this field element. So I'm going to use multiplicative notation here, but this would be an elliptic curve group, so additive notation is more common. Then in order to sign a message, the signer is going to sample a nonce, a number used once uniformly at random, and then form a commitment to this nonce, which is this capital R. They're then going to form a challenge in the terminology of the Schnorr identification scheme, which is a hash that takes as input the public key, the message, and the nonce that's used. Then the signature is the nonce plus the challenge hash value multiplied by the secret key. So here the nonce essentially blinds the secret key. And again, it's sampled every time you issue a signature. Verification checks the hash value and then this equation, which as you can see, looks exactly like the equation for Z. The main security property for digital signatures in general is unforgeability. So if an adversary can see polynomially many signatures on messages of its choosing, it should not be able to forge a signature. Now, when building multi-party Schnorr schemes, we want to take a closer look at the structure of this equation. So we want a way to distribute the secret signing key, which I've talked about. For the purposes of this talk, I'm going to assume trusted key generation, so you can think of Shamir secret sharing. But we also need some way to share this nonce, because if any party possesses this nonce, then they can trivially extract the secret key. So the idea of Stinson and Strobel, as I mentioned, was to use a DKG for the nonce. But this means that you're running a DKG every time you sign, and so this incurs multiple signing rounds. So what we're interested in here is coming up with a more efficient way to do this. Let's begin by looking at how we might construct a 2-round threshold Schnorr scheme. So here, again, the signing parties will engage in some key generation protocol, just think of Shamir secret sharing, and then they will each produce their Schnorr nonce. In the first round, the parties can output their nonces. And for the sake of simplicity, I'm going to assume that there is a combiner. You could have broadcast, but the combiner can be any party. It doesn't have to be trusted for enforceability. Here, for simplicity, the combiner and verifier are actually going to be the same party. So they output the nonces, and then everybody takes as input everyone else's nonces, and they simply form the aggregate nonce as the product of the 2 nonces. And then the challenge hash is formed as the public key representing the set of n signers, the message to be signed, and the aggregate nonce. Then each party produces a Schnorr signature. Note here, though, that we do have the Lagrange coefficients for the threshold signing. In round 2, the parties will simply output these partial signature shares, and the combiner can add these values together and then form the hash of, again, the aggregate public key message nonce and check the equation, which is exactly standard single party Schnorr. The problem with this construction is that it is not concurrently secure. This was actually the first attempt at 2-round multi-party Schnorr schemes, but there are a number of works that show that this is insecure. So for a concurrent adversary, they can open multiple signing sessions at once. And here I'm going to consider a simple scenario where there are simply 2 parties, 1 adversary and 1 signing party. This was exactly the scenario considered by the paper in 2003. So the adversary can open, say, K signing sessions at once with Alice. And in our construction, in the first round, parties output their nonces. So the adversary can basically open K signing sessions and wait and see the honest party's nonces before determining their own nonces. And so this rushing adversary can actually forge a signature. And the forgery relies on a kind of birthday attack, because it's based on the hash that takes as input the public key message and nonce. And you can basically find collisions in that. And you can find these follow-up works show that you can produce these forgeries in polynomial time with greater than 256 sessions. These attacks were devastating for a number of threshold signatures, multi-signatures, blind signatures. And the solution is basically just to force the adversary to commit to their nonce. So they can't wait to see the honest party's nonces to determine their own. Enter Sparkle. So Sparkle is a 3-round Schnorr threshold signature scheme. And to begin with, parties run key generation as usual and sample their nonces. But in the first round, they instead commit to not just their nonces, but also the message and signing set. So they form these hashes and then output them in the first round. In the second round, the parties will then reveal their nonces. And then at this point, they can compute as in these 2-round schemes. So simply multiply the nonces together, compute the hash and the partial signature shares. They reveal these in round 3, and verification is as before. This scheme is concurrently secure, again, because we're preventing the adversary from waiting to see the honest nonces. But I want to point out that actually it's concurrently secure even if the message and signing set are given in the second round. So it's a bit counterintuitive to look at this, because the message and signing set aren't actually really used until the third round. But to prevent a concurrent adversary from forging, we need to give it in the second round. And one of the main observations of this work is in order to achieve adaptive security, we needed to give the message and signing set in the first round. So we're basically pushing these values up in the rounds in order to achieve these stronger notions of security. Okay, I mentioned some multi-party Schnorr schemes at the beginning, but I'd like to focus in on some recent work. So we have the 2-round schemes, Frost and Frost 2. These are secure under the one more discrete logarithm assumption in the random oracle model. We also see a number of 3-round schemes, which all follow the similar commit reveal style. And the scheme by Lindell is in the UC framework and is based on a functionality for single party Schnorr signatures. Classic Schnorr is based on a threshold functionality. And Sparkle is proven in a game-based setting under the discrete logarithm assumption in the random oracle model for static security. So all of these schemes are concurrently secure, but none of them achieve adaptive security. Classic Schnorr uses a guessing argument, which I'll talk about a little bit later, but this incurs exponential loss. So we prove adaptive security of Sparkle, and we also prove that the reduction is tight. Okay, so what is adaptive security? When we prove the security of threshold Schnorr schemes, we typically prove, or actually threshold schemes in general, we prove them under static unforgeability. What this means is that the adversary has to choose which parties it's going to corrupt at the onset of the protocol before seeing any other messages. But the stronger adaptive adversary can actually corrupt parties at the beginning as well as the protocol progresses. Again, thinking multiple signing rounds, multiple sessions. And the thing is that at the point at which the adversary corrupts a party, you have to reveal that party's secret key, but you also have to reveal their state. And this is really challenging, especially given the complexity of the protocols that they're involved in. So to take a closer look at this, an adversary could potentially open multiple signing sessions, which could be involving different signers. They could be in different rounds, have output different values. And if Carol here is corrupted at this point, we need to be able to simulate in such a way that we can output these values in a consistent way, but without knowing the challenge secret keys that we're working with. So adaptive security is challenging. It is fairly straightforward to achieve via guessing arguments. So this is kind of a standard technique for taking a statically secure scheme and translating it into an adaptive scheme. And basically it just relies on the reduction guessing which parties are going to be corrupted and then aborting if they're wrong. But this incurs exponential loss, so n choose t loss. You could also use tools like non-committing encryption, or we could require the secure erasure of secret state. So these are some tools that have been used in the past. But requiring secure erasure of secret state, if it's required for the reduction to work, it just isn't feasible to implement in practice. What we're interested in is adaptive security for a large number of parties, and there are a couple of reasons for this. I choose n greater than 1024 because the NIST document specifies different classifications for numbers of parties. So if you had 1 to 8 parties, it would be really easy to just use the guessing argument. But as you get more and more parties, it's more difficult. We want large n because, again, these schemes are being used in practice, and notably to secure cryptocurrency wallets where you may feasibly have a large number of parties. We also want to make sure that that n is large to prevent an adversary from corrupting a majority. Okay, so here are our results on Sparkle. We first show static unforgeability under the discrete logarithm assumption in the random oracle model. And we have 2 adaptive results. So the first one is T/2 adaptivity. And the reason for this is that we use a rewinding argument. So the reduction runs the adversary once, and then it rewinds the adversary and runs it again. And if the adversary can corrupt more than T/2 parties in each of those sessions, then they just simply have enough values to extract the secret key. Now, I will point out that this reduction using rewinding actually doesn't incur any security loss more than the standard reduction for Schnorr under discrete log. And our strongest adaptive result is showing full adaptive security of Sparkle. So what this means is that the adversary can adaptively corrupt T out of the threshold of T+1 parties. We show this under the one more discrete logarithm assumption and in the algebraic group model. And again, we achieve the adaptive security in conjunction with concurrent security. I'll just give a quick overview of how the reduction works. So the reduction is going to take as input one more discrete logarithm challenge. So this is a set of t+1 values, and the reduction's goal is to output the discrete logarithm of all of these values. So it first needs to form the public key representing the set of n signers, and also produce the public keys for each of the signers. It then passes these values to the adversary, and then the adversary can engage in concurrent sessions. They can have parties participating in different rounds. And at some point, the adversary says, okay, I want to corrupt party I. Well, the reduction can simply use its discrete logarithm oracle in order to retrieve this value. So it goes to the oracle, it says, give me the secret key. But now the reduction needs to hand not only the secret key over to the adversary, but also the state for everything that has happened with that party so far. At the end, the reduction wins if it outputs this set of discrete logarithms for its challenge. There are two main challenges in doing this. So the first is that, well, you have this discrete logarithm oracle as part of the OMDL assumption. You simply use it, get the secret keys, but you can only do that t times. You have to get the one more discrete logarithm. So this means that somehow we need to come up with a way to extract this value, either by rewinding or in the AGM. And more importantly, it's very difficult to simulate state. Again, parties are running 3 signing rounds, as many sessions as the adversary wants to open. So how do you do that consistently as a reduction when you don't know all of the secret key values? So this is kind of the main technical challenge of this work. Okay, so key takeaways. Adaptive security is a very important property to achieve. These schemes are being deployed. It's included in the NIST document because it's a very, very important requirement. It's also quite challenging to achieve, but we do show the first fully adaptive security proof for a Schnorr threshold signature scheme, and moreover, the reduction is tight. Again, the main challenges are that we have multiple parties, multiple signing rounds, concurrent security, which broke most of the schemes just a few years ago, and adaptive security, which is a well-known difficult problem. So combining all of these things together and achieving the security was very challenging. And it has to look like standard single party Schnorr at the end. So these are all of the requirements and specifications that led to this work. I'd also like to point out that we are working on adaptive security proof for Frost. And that's it. Thank you.
All right, do we have any questions? I see somebody walking up to the microphone. Yes.
Hello, thank you
Hi.
for the great presentation and for looking at adaptive security. Do you believe that the protocol as is strongly enforceable?
Strongly enforceable.
Yes. And
Yes. Yes, I do. I think that I think, yeah, so for strong enforgeability, we already have this for Frost, of course. For Sparkle, we didn't show strong enforgeability, but it's straightforward to add. I don't expect any challenges there.
thank you.
We have maybe a second question. Yes. Go ahead.
The protocol is not this scheme is not robust, right?
No.
So how do you work with large N?
So the protocol is not robust. None of these schemes are robust. There are methods for translating these schemes into robust schemes. So there's roast as an example. But basically what's used is you just abort. You can have identifiable aborts, so you can tell from the partial signatures who's misbehaving, and then you just kick that party out and rerun it. But there are ways of translating these schemes into a robust setting, which we don't cover in this work.
But the identified abort itself doesn't work with large N, because just 1 out of 1,000 will not send you the stuff, and you have to start again.
Yeah, I think the issue of robustness, though, is just a separate topic, which is also interesting. But yeah, we don't achieve robustness in this work.
Maybe a more practical question. Do you have plans to implement it in any specific place?
Yes, we do. So we will be submitting some of these schemes to the NIST standardization process. So we will be coming up with implementations. There are a number of implementations already available for schemes like Frost, Music2, not yet for Sparkle, except for my own terrible Python implementation. So they will be implemented in the future, yes.
Great, fantastic. Any further questions? No? Oh, Evgeny, maybe?
Sorry, maybe I misunderstood the last slide. So you have a fully concurrent, like fully adaptive security under in AGM, you said, or algebraic group model?
Yeah, fully adaptive into the AGM. Actually, I forgot to mention one point, which is important. So the fully adaptive proof is in the AGM, but it actually relies on a weaker form of OMDL called the algebraic one more discrete logarithm assumption. So this is not like, it's not in the AGM, like we can use the T/2 adaptive proof is also using this assumption. But what's interesting about it is that it's actually falsifiable because the discrete logarithm oracle is PPT. Because the submissions that the reduction is making to its discrete logarithm oracle are actually just linear combinations of the challenge elements. So that discrete logarithm oracle is actually PPT, fully falsifiable. I meant to mention that. But it does use the AGM for the full adaptive.
And I just wanted to check because once you use AGM, do you actually need? I think it's nice that you kind of separate extra assumption, but once you use AGM, do you need extra assumptions? Why do you need? Can't you like just prove it in AGM? Whatever this one more.
What do you mean extra assumptions? Like
well, like in AGM, you can just prove that one more discrete log is just true, right? In AGM model, or that's my question. But usually, like discrete log and things like that.
OMDL plus the AGM, yeah. But we can use the weaker form of OMDL.
So I guess my question is why? Just maybe, right? Because in all those like ideal model, you can just prove discrete log is true, like in generic group model, right? And
yeah,
so this one more just doesn't work.
Yeah, we need the one more to get those secret keys. So I don't know how you would do it with just the AGM straight.
Okay.
Yeah.
Okay, well, I think we ran out of questions. So now let's thank all the speakers again for all these best papers. And I